Dr. Lee is an associate professor in sustainable bioenergy at the University of Maine, and the floor is yours, please.
Good morning, everyone. I'm very happy to be here. First, I would like to thank Professor Hu inviting me being here to give a talk about our research regarding our research on advanced wood products in sustainable building systems. So it covers the product development, assembly design, performance assessment, and simulation. So here you can see I underscore the two names, myself and my PhD student, Ling O'Brien. So this talk will include two sections. The first section, I will give an overview about who we are and what we can do. And then I will hand it over to Ling. So he will talk about the specific project he works on that. So can we go to the next slide? Oh, okay, I can do that, sorry. Yeah, so here, so at UMaine, we have formed an informal alliance called Building Efficiency Science and Technology Group. So acronym is BEST Group. So here you can see we have a lot of people from School of Further Resources, Wood Composite Center at Advanced Structures, Wood Composite team from the Advanced Structures and Composite Center, and Mechanical and Computer Engineering. So here we can do material and product development, including composites and porous laminate timber. And also we can test the product and material properties following standard and non-standard methods, and also do material property characterization. And the following one, we can design assemblies for roof and wall applications in different building types. And then we have a whole building simulation and monitoring capabilities. So I got permission from Wood Composite team at Advanced Structure Composite Center, so I can present their research capabilities there. So from here, you can see Composite Center has the first pilot scale fiber line, so which can provide a research R&D regarding the pilot scale composites products production in a variety range from wood fiber insulation, low density fiberboard, medium density fiberboard, and even to the high density fiberboard and particle boards, something like that. So also we have a mass timber commercialization center. So there we have the capacity to design, fabricate, and testing the full scale CRT panel products. About the wood fiber insulation and cross-laminated timber applications. So we developed wood fiber insulation panels. So as you can see, these wood fiber insulation panels are made of wood fiber insulation adhesively bonded with cross-laminated timber compared with current technologies. So they are highly thermally insulated panel products without any metal fasteners for connections. It can greatly reduce the material cost by 30 to 40% based on the cost analysis from our collaborators. And also its airtightness, and also it can be achieved for panelization manufacturing at the offset manufacturing plants. So having those wood fiber insulation materials and mass timber products, so we can do material characterization to get the first-hand information for our modeling simulation. So once we design the roof and wall assemblies. So we have built this nature exposure facilities on campus. So this natural exposure facility is located in the unique climate zone. This is climate zone 6A. It has a long, harsh winter season, so we can test the thermal performance of wall and roof assemblies. So we can do hydrothermal durability simulation and building energy consumption simulation using Woofy software and also Design Builder embedded with Energy Plus. And this one is an ongoing project. We have been doing that for 4 years, since 2021. So we put sensors into a school building at Belfast, Maine. We monitored the hydrothermal performance and energy consumption of this wood fiber insulation CLT school building for 4 years. So Ling will come over here to talk about the detailed results based on the 4-year monitoring period. Okay.
Thank you. Yeah, so I'm just going to spend the next couple of minutes discussing some of the work that we've been doing on that school building specifically. So just to start, we're looking at a CLT and wood fiber insulation building. And some of the reasons that we're interested in this is that the building envelope is one of the most important things in the structure of the building, right? It could greatly impact interior comfort, air quality, and thermal separation and durability. And so looking at that, using wood fiber insulation and CLT, these are two hygroscopic materials which can absorb and desorb moisture from the water vapor and under real conditions and reduce RH spikes, temperature spikes, things like that. And current guidance in using CLT is focused on fossil-based or mineral-based insulation types. So there's not really much experience using wood fiber insulation with cross-laminated timber. And considering that, these materials are sensitive to water and water vapor. And so improper design can lead to increased risk. And so we want to make sure that when we implement these building materials, they can stand the test of time. So Ling mentioned that we're looking at the Corner Spring building in Belfast. So right here's just a little overview. Let's see if it plays. It's a panelized building. It's about 1,000 square feet or 90 square meters. And in this video, it's a short overview of how this was assembled. And so it was panelized off-site in a factory setting where they brought in the CLT and wood fiber insulation, laid it out, cut it, screwed it together. And this process that you're looking at right now took about a month and a half's time. And you'll see they add up the CLT and start to put their WRB or their water resistant barrier on top of that. And that's one of the actual interesting parts about this building here. So typically when we look at cross-laminated timber with those fossil-based insulation types, your water-resistant barrier will be put underneath the insulation at that CLT interface. But you can see here they're putting it on the outside. And that's because of the panelized process. So this will allow them to bring these panels on site and attach that water-resistant barrier to the exterior, creating a bulk moisture layer where they don't have to be concerned about it. And during this process, we were able to stop by. I don't know if you guys saw any blue hard hats, but that's when we were installing sensors. And so when they brought the panels on site, this took about 2 days to put together. So they spent about a month and a half putting it in the factory and only 2 days actually assembling the structure. And after that 2-day period, the structure was watertight, and then they finished it up in about a month's time. And as you can see, the windows were installed in the factory. However, the doors were not. And as they've done more buildings, this was their first. Their time has been reduced actually, so it no longer takes about a month and a half, and only takes a few weeks. And if you notice, again, it's a small footprint. There's actually only 2 main buildings. It's a school building, and this is an annex. So there are 2 classrooms, a main entryway, which students enter in and out of and can get to the 2 classrooms, and a bathroom, and that's really it. And I think this is the last panel here, and we'll start to see some of the roof assemblies. These are all put together with these long fasteners, about 9 to 15 inches long, depending if it's the wall or roof assembly. And yeah, there you can see it's very thick. And then these panels are screwed together with a lap joint down at the site CLT from the inside as well. And that's what connects everything together. And again, small building next to the larger building right there. And so we mentioned that this is a small school building in Climate Zone 6A in Belfast, Maine. So that's what you could see on the left there. It's about a 6.5-hour drive from here. Pretty cold winters, pretty moderate summers. So you can see down on the left here are degree days, a lot of heating degree days, so a lot of heating energy used, but not very much cooling energy used. And when we were instrumenting the building, on the right here, we did so at different layers throughout the assembly. So there are multiple layers of wood fiber insulation. And so at each interface from the left to right, we installed temperature and relative humidity sensors, as well as moisture content sensors in the CLT. And the same goes for the roof. We also install them at different densities throughout the building. So all these dots represent sensor clusters. We see those buildups throughout the building. The red ones are primary sensor clusters, which have a higher density throughout the entire envelope, each layer. And the blue ones are lower density clusters, which are just at the interior and exterior of the envelope. And so just a quick to show you some of the monitoring data. The top cluster of lines is relative humidity, and the bottom cluster of lines is temperature on each axis. But essentially what we see throughout the thickness of the wall assembly, from the interior to exterior, you see interior conditions remain fairly stable compared to the exterior for both temperature and relative humidity. And then in the both north and south orientation, you'd see what you'd expect. Higher moisture loads in the north, slightly higher moisture loads in the north than the south, and slightly lower temperatures in the north than the south. And here's some of our moisture content data at that middle lamina of the CLT. And so first thing to point out is we have these 2 dotted lines. Those are some sensors that we found were faulty. But after that, we could just generally get some trends and see that the moisture content at the beginning of the monitoring period is slightly higher than later on. And it follows cyclic trends, which match the local climate, where moisture content's higher in the summer and slightly lower in the winter. And so what we could do is take the wall assembly and those measured material properties that Dr. Lee had mentioned before and put them into a hygrothermal model. And for this, we used Woofy software and built up our wall assembly exactly as it's seen before: cross-laminated timber, wood fiber insulation, WRB air gap siding. And then you take that simulated data over our time period and compare it with our monitoring data. And so that's what we did. And so I'm going to show you results for 2 monitoring positions just in the north wall. And so this is what we call P1, the innermost position. It's a CLT to wood fiber insulation interface. And we can see in our simulated data is in green and our measured data is in black. And overall, on the left, it's the entire period. We see good general trends. As we start to zoom in on our 3 weeks in the summer and 3 weeks in the winter for both temperature and relative humidity, we start to see that there are differences between our measured and simulated. And so what we found was that's actually due to some of our interior conditions, which I'll talk about in a second. And the exact opposite is true for the P3, that exterior position. So this monitoring position is just wood fiber insulation directly under the WRB. So there's not really much separation between the exterior climate and this monitoring position. And we see both for our short term and our long term, there's good agreement between our simulation and measurement. And so we're able to take that and then use our calibrated model to simulate this over a 5-year period to determine a mold growth assessment. And to do that, we used a different software program looking at a mold growth index. And you'll notice on the left here, you could see in red a threshold. And that's the line we can't cross at our positions. And you also notice that it doesn't really look like there's that much on the graph. But that's because we really didn't have any risk of mold growth throughout the period. So we never crossed the threshold. And on the right, you can see how low it is. If our mold growth index is 3, the highest we ever reached is 0.075. So it passed in all of our conditions within the wall assembly for both the monitoring and simulated period. And when we were instrumenting the building with our temperature and relative humidity sensors, we were able to install an energy use tracker. And so we're able to see general trends that match the occupancy in the building. It's a school building, so it's only occupied from August to June. And it's only done so by a few students, 5 to 10 students at a time. So we could see this is an energy consumption graph right here over a few different years. And we can map generally when students are in session. And it matches the general load. And so again, we could take our building design and the energy data that we have and use that to inform an energy model. So we'll develop an energy model using Energy Plus and Design Builder, simulate that over our measurement period, and see if there are any changes that we can make to the building to improve the energy performance. And so looking at this graph on the left, we have our measured and model data. Measured is in the black bars and model is in the light bars, the gray, the multicolor bar. And you can see there's a big difference in a few months. So essentially, when we were looking at our energy use, it matches the trends of occupation, but according to our model, it shouldn't necessarily do so. And we should see drastic drops in our heating and cooling load during transition months. So during the summer, we should see high energy or higher energy use because of cooling. And in the winter, cold months, we should also see high energy use because of heating. But those in between months, we should see a drop in load. But we don't. And so what we started to do was have conversations with the people who are in the building, the students and the instructor there, and look at some of our data. And we started to notice that there are large temperature variations of the indoor conditions. And so in having those conversations, we found out that the building temperature drops very quickly when the doors open, and students have to go in and out frequently. It's a classroom that's an annex building, so if they have to go to the main building, and it'll drop the temperature in the building very fast. So unfortunately, we found out that our energy consumption was dominated by space condition, and the space conditions were changing very quickly as that door opened and closed. And we can't really predict the use because it's door opening and not window opening or something like that. We also found out that our interior temperature sensor, where they were using it for some group projects, and so it would be moved around the building. So some days it would be in the sunlight, some days it's not, which also affects the temperature stratification in there. And so, like you said, our loads are largely dominated by heating and cooling. And so this is our simulated data. And we had some conversations with the building manager, and this is a theoretical load, right? Theoretically, they could reduce their energy consumption by about 25% if they were to change some of their use cases or their occupancy schedules. And so what we chatted with them about was seeing if we can control some of that change in natural ventilation. And hopefully in the future, we'll be able to see their simulated results match the model results more closely or some different changes. But what we're finding is that when we develop these create these high performance buildings, we also need to focus on helping people how to use these buildings and making sure that when they're used, we can reach their targets without creating an energy efficiency gap, essentially. And so just to wrap up, we were able to find our agreement between our hydrothermal model and our measured results, and that our interior conditions were variable. So we had better agreement with the exterior positions than the interior positions. But overall, we found that there was no mold or fungal risk with this wall assembly in that cold climate, and that occupant behavior had a large impact on energy consumption. And so we're hoping that our future work and some of the other work in Dr. Lee's lab will help to solve some of these problems, focusing on efficiency, durability, safety, and resilience with building products. And if you're interested in learning about any more of what we just chatted about, these are some of the publications that those are based on, starting with a literature review, going to a couple different case studies in energy occupancy. And I'd be more than happy to chat with you guys more if anyone's interested. And just wanted to say a quick thank you to our sponsors and see if there's any questions or wrap up. Thank you.
Thank you both, Ian and Leah. We have, do you have a half a question each or one question?
I grew up on the East Coast and moved off to school. Wood fibers on top of the CLT, right?
Yes.
So you get a lot of snow there?
Yes, yeah, definitely a lot of snow. Yeah, so the CLT in the walls is a 3-layer CLT or 3-ply, and on the roof it's a 5-ply. The wood fiber insulation that is used has a fairly high density, 140 kilograms per meter cube. So it's has more compressive force than like a cellulosic or like your mineral wool. So it's denser than most people think. So like you could walk on it and it's not a problem. And they haven't seen any issues yet. So
yes, we have time for one more question.
Have you done a comparison with just the standard stick build house performance? And another follow-up is that is this build at the code plus installation performance, or you're just trying to meet the minimum code?
Yeah, it's a great question. So that build, and I apologize for not mentioning it, it is very, very far past code. So a code requirement in Maine, I believe, is about an R21 wall, and that wall assembly is at an R40, so almost double. Roof assembly is near an R40. That roof assembly is near an R70. For this building, we haven't specifically looked at a code comparison or a stick built comparison, but for one of the other projects that Dr. Lee mentioned, the development of wall assemblies we have, and we have seen greater performance from that CLT, assuming it's to mass storage and thermal storage or heat storage. But I don't have a great answer. Yeah, we have been working on it, but isn't included here.
This is mainly to specify people WUPI and other models.
Yeah.
Well, thank you both of you once again.
Thank you.